Good evening, everyone. It's great to see so many people here discussing what I think is one of the biggest challenges, really, of our time. And I have a small part to play in that, and I hope to, in a sense, focus a discussion today on what we can achieve, as well as looking at some of these issues of problems that at the moment we cannot solve. So, I mean, where do we start? We start with today, and we start with this morning. This morning, like many of you have done, I've looked at the human population counter, and rapidly it goes up even as you look at it, but you quickly freeze it and put it on your slide. I mean, it's 7.2 billion people at the moment and rising rapidly. Compare that then with those who are going to eat, with what they're going to eat, and we're at almost 4 billion tons of food, that's vegetables, grains, meats, and dairy, that are produced per year. And if we stack those up in a very coarse and gross way, that is equivalent to 2,700 calories per person per day. So that's fractionally over the nutritional requirements of a normal-sized adult male. In other words, there is already enough food to go around if it were to be, in a theoretical way, spread around the world in an equal an equivalent amount. However, and this is the bit where my work at DFID comes in, the bottom line on this particular slide is there's still 850 million people undernourished and perhaps 1 billion or so suffering from some kind of micronutrient deficiency. Now, it should be said that technologies have had a big part to play in getting us to that place. Most of us are familiar with the Green Revolution of the 60s and the 70s that produced new and improved varieties of maize, of rice, and of wheat, and all the sort of technological techniques that used to grow them more efficiently, and took hundreds of millions of people across Asia mainly out of poverty and out of hunger. So agricultural technologies have played a part in getting us to where we are. Now, if we are to look forward, then what is the challenge? Well, of course, the title of the presentations today is Feeding the 9 billion. And the mid-range UN projection of the population by 2050 is 9.2 million people, with some big errors around that, but that's the central estimate. And those who have taken this approach of counting up how much food we need to produce tell us that we need to produce, as a globe, about 70% more food. But Jay has already mentioned the increased dietary choices and dietary requirements of the growing middle class, principally across the BRIC nations as we know them, and then the change in where people will live that will require our food delivery systems to deliver into massive urban areas, more so than they do now. And then the additional challenge of climate change, which for some parts of the world, in fact where we are now, in the next 20 or 30 years will result in an increase in production, but across many parts of Africa and Asia will be an additional threat to this challenge of feeding the 9.2 billion population. So I've been asked to try to outline the role that agricultural technologies might play in trying to crack this problem. And I should say at the outset that the technology silver bullet does not exist. This is not purely a technology problem. You can see from the today box there that with all the technologies we've got, there's still a big access and distribution problem when we look at the global supply and demand for food. So this is not a perfect solution. What I thought I would do is spend the next 8 or so minutes showing you 5 agricultural technologies that are being developed now that at least chip in to this challenge of feeding the 9.2 billion. So let's start with one that, by coincidence, has the most catchy name. This is scuba rice. Okay, why is it called scuba rice? Well, rice, in the most part, is grown within paddies, but rather strangely, if the water goes over the top of the rice, it essentially drowns. Rice can only survive 7 days or so underneath floodwaters, and then it will die because the oxygen won't get to the roots. Now, in India and Bangladesh, intermittent flooding kills about 4 million hectares of rice each year, enough rice to feed 30 million people on average every year. Now, in the 1970s, someone at the International Rice Institute in the Philippines discovered that there was a wild type, a progenitor type of rice that could survive submersion for longer than standard rice. In fact, it could live underwater for 17 days, and then when the floodwaters recede, it will grow again instead of lying there dead. He didn't term the term scuba rice, but in the mid-90s, renewed interest was generated in this sort of rice, and the genes that control that characteristic were transferred out of the original rice variety and put into modern varieties that are grown across Asia. In fact, put into the mega varieties, as they're called. We have Swami rice that's on the left here that survived 15 days of flooding. Rice that, without this submergence characteristic, that's been brought in by natural selection from one of these old ancestors, it wouldn't survive. How important is this? Well, about 100,000 farmers across India are now growing this Scuba rice, as it's called. They now have resilience to these flooding events. And the target of the International Rice Research Institute that is still putting out this rice as a global public good is to meet 18 million farmers with the Scuba rice types. Let's move to a livestock example. There's a disease of livestock, cattle plague, that's called rinderpest. There's a measles-like virus. It kills 95% of cows that it infects. It leaves them with fever, with severe dehydration, and in 7 to 10 days, they are dead. Now, ever since cattle was domesticated 10,000 years ago, the rinderpest virus has been around and has been a plague on many different cattle production areas, including in Europe. In the 1950s, a vaccine was found for rinderpest. In a sense, that took care of some of the rinderpest outbreaks in temperate areas, but it wasn't until the 1980s when a heat-stable version of the vaccine was developed that the rinderpest eradication in the tropics began in earnest. Now, about 15 years since that vaccine became available, when it was combined with community health initiatives, with disease surveillance operations, we've now eradicated rinderpest from the face of the earth. There are 157 countries that are now rinderpest free, and this is one of the very, very few viruses, human or animal, that have been eradicated. Let me move to my third example, and this is a rather traditional example. This is a tree called Phyherbia. You notice it fails the catchy name test that Scuba rice has. The Latin name is Phyherbia albina. It is a traditional African tree. It is a legume. It is called apple ring acacia and about a dozen other names in English. It is very unusual. For some reason, it holds its leaves during the dry season. It drops them during the rainy season because it has a very deep taproot. It can access water reserves in the groundwater, and during the rainy season, for some reason, it then drops its leaves. Why is this good? Well, what this means is you can grow a crop underneath. And in this image here, we have a maize crop growing underneath the Phyherbia tree. It's benefiting from the nitrogen that's in the leaf that's falling into the soil. It has enabled Zambian farmers to increase their yields from 1.3 tons per hectare to 4.1 tons per hectare. It is a natural tree. It is spread by farmers taking cuttings, planting cuttings in nurseries, and then distributing the tree to colleagues. There are now 160,000 farmers in Zambia growing their maize crops underneath this tree, and it's contributing to the regreening of almost 5 million hectares in Niger. It is bringing what is otherwise poor, fertile soil back into production for these farmers. And let's go to number 4. And again, I'm trying to pick different examples as we go along. Here's an example of information from satellites orbiting the Earth being used to provide an insurance product for pastoralists in the very dry areas of Kenya and Ethiopia. What has been developed is an index-linked product that links the greenness of the surface that's sensed by the satellite to the number of livestock that die essentially under dry conditions, so in the years when the rains fail. This is very much at the pilot scale, so unlike the other examples I've given, I can't give you hundreds of thousands or millions of hectares, but this scheme has been running for 3 years, and to show that it worked, and 2 of the last 3 years it's paid out to smallholder pastoralist policyholders who have taken up this insurance, because for them, their livestock is not only a source of income, but it is their main asset. It is their bank, in a sense, for these communities. And so they have a way of, admittedly relatively expensive, but they have a way, they have an option of trying to hedge against those drier than average years. And Jay, moving to the last example, what I've covered so far has been about quantity of food. Now this is about nutrition of food, and speaks almost to your cassava example in one of your images from Rwanda. This is orange flesh sweet potato. So sweet potato that we're all familiar with is one of the main root crops that's grown and consumed across Africa. It has a lot of starch, but it doesn't have a lot of nutrition. However, one of the sweet potato varieties is very rich in beta-carotene, a precursor of vitamin A, And vitamin A deficiency affects almost 500,000 children under 5 across Africa, leading to blindness and in some cases to death. So what scientists in America then have done is transferred, again using conventional breeding techniques, this vitamin A precursor into a sweet potato variety, and into a sweet potato variety that consumers, farmers, and those buying these in small-scale markets actually choose to buy, not into some new highly bred variety. So as a result of this, the consumption of only 100 grams of this orange-stressed sweet potato provides a child under 5 with sufficient vitamin A to fulfill his or her daily requirement. It's now consumed by 500,000 farmers across South and Southeast Africa. So let me repeat as my final word, my word of caution: agricultural technologies are not the silver bullet to feeding the 9 billion or so, but they have a part to play. And if all of you in this room are UK taxpayers, then you also have a part, because this, in a sense, reflects the contribution of your tax dollars into agricultural research technologies. Thank you very much.
Thank you. I'm a big believer in technology, but it not being the silver bullet. There was an interesting paper earlier this year by somebody I believe you know, Pete Smith up at Aberdeen, in which he was looking at all the possible technological advances that could be made to advance the possibility of complete food security. And his conclusion that it was only about a quarter as effective as a proper change in nutritional behavior by the world's population. Is there a strong point there that actually we could probably solve a lot of our problems depending on how we consume rather than what we're growing?
I think the point that he's making is essentially this is a complex problem, and it has many facets. I think it would be difficult to argue that you shouldn't be pursuing one option because it's only part of the solution. So my overall response would be, fine, let's look at all the options, let's pursue as many as we can, and there'll be economic incentives for doing some, and others will need proper financial support. But let's not just rule anything out because it's not the best and the most cost-effective thing to do. Let's sort of celebrate the diversity of options.
Don't let
keep them all on board.
Good be the enemy of perfect.
Perhaps. I'll think on that.
Can I just say, by the way, for those tweeting, the hashtag is #CC21, and feel free to tweet at will. Tim, thank you very much.